But if du dt is less than 0, then that means that the absolute value of du dt is minus du dt, right? And it also means the bounds are flipped because it's a decreasing function. So it flips the bounds. And so it's kind of cool. So you get the 1 minus from this, right? And then you flip the bounds because it's decreasing, and then you have to flip them back. That minus cancels the other minus, and we're still getting the same arc length integral. This proves for you that the arc length integral is independent of the orientation of the curve which you're integrating over. So whether you go from point P to point Q or whether you go from point Q to point P, the arc length integral is the same. Which makes sense, right? Because we're calculating like the area of this curtain or the net amount of stuff along a curve. You're like, what's the mass of the line of what's the mass of the curve that goes from point 1, 2, 3 to point 4, 5, 6? You're like, wait a second. Are you sure it's not the curve from point 4, 5, 6 to 1, 2, 3? No, you wouldn't ask this, right? I mean, like the mass of some curve through space is whatever it is. It shouldn't depend on how you orient the curve that you're describing, right? I mean, that's crazy. And the math, in fact, bears that out. Most people have the good sense to not prove this in class, but I think it's important. Because we're going to study a line integral of a vector field later in this course, and that's going to depend on the orientation. Flipping the orientation is going to flip the sign of the integral. This is not that, though. And here's a nutshell. What we just proved is that the arc length along the curve is equal. The arc length integral of FDS along the curve is equal to the arc length integral of FDS along the reversal of the curve. We have just proved that in gory, stupid detail. Uh-oh, I broke him. I said I broke you. Sorry.
3 hours of sleep.
3 hours of sleep. Yeah, it's not quite enough. 4 hours is good, but 3 is, so in gory here, so like pragmatically, you've got a curve in 3 dimensions. You've got a function of 3 variables, f of x, y, z. How does this actually work out? We're saying integrate from a to b, f of x, y, z, and then the square root of x dot squared plus y dot squared plus z dot squared. This is what we have to calculate, but this still doesn't do it justice, right? Because this x, y, and z, you have to plug in the parametric formulas for x, y, and z to actually calculate this, right? Hopefully I have an example. Here's an example. Suppose we look at the linear mass density of a helix, one of our favorite curves. Our cosine t, our sine t is equals to t. And I'm going to give us the mass per unit, the mass dm dz. Oh man, I want this to be, this is a typo, guys. What should this be? That should be ds. Yeah, that's what I mean there. So the mass per unit arc length is given by z. What that means is like it's a lumpy helix, right? I mean, like it starts out like really thin, but as it goes up, it gets like thicker and thicker and thicker, right? So like it's, I don't know, it's a weird helix, but.
Or just denser and denser and denser.
Or sure, if you wanted to make it denser. So the total mass
starts with hydrogen.
So
goes to osmium.
This is not chemistry.
I can make it chemistry. I can make anything chemistry.
From 0 to 4 pi, from 0 to 4 pi, this gives us two revolutions of the helix, right? Once and then again. I can't do that. Once and then, yeah, like so that. So to calculate the total mass, I should integrate from 0 to 4 pi, this, right? Now z, why do I put, so this z is not z, right? I'm not done yet. What is z? Z is equal to t along this curve. So that's why I plug in a t right here, right? The speed is r squared plus 1. And so we do the integral, and we get 8 pi squared, square root of r squared plus 1. Yep.
Just wanted to make sure.
Yes, that is not how you spell contrast, but anyway, go on.
No, I didn't do it, but z equals to t is correct. It's just the dm dz.
Yeah, this is, that's supposed to be dm ds.
Okay, but the other z is correct.
Yes. I mean, for a helix, we parameter z equals t, just makes the helix, it's a linear helix with slope 1. It goes, you know, it's.
Okay.
But the interesting thing here, of course, is that when we do this integral, we have to plug in the formula for z for the curve, which in this case is just t. And anyway, that's the total mass. What's the arc length? How do we've already talked about arc length in here, right? But this integral with respect to arc length reproduces the arc length formula if we take a very special thing. Just take the function to be 1, right? Then the integral of ds is just s, as it ought to be, right? Like notationally. So like the arc length is just integrate ds along the curve. That make sense? I hope it does. So the arc length of this helix is that. So anyway, just there it is. So if you wanted to calculate the average mass density on the curve, you could take the total mass divided by the total length. That would give you the average mass density, in contrast to the infinitesimal density, which is variable. Now, you guys remember, the other thing, of course, we can do is we can calculate the average of a function along a curve, right? So to calculate the average of a function along a curve, what you do is you do the scalar integral of the function along the curve, and you divide by the length of the curve. That gives you the average of the function along the curve. So there you go. So like for the last one, the average mass would be 1 over L times that. From the previous example, I calculated this integral is that. That's the arc length. So the average mass per unit length is 2 pi, as it happens. Another important application to physics is you can calculate the centroid of a curve. All right. So the centroid of a curve, what you got to do, the center of mass rather. What's the difference between centroid and center of mass? I think if I'm going to project my notes, I need to choose some. I love green. That's why I put my definitions in green. But these projectors always let me down in terms of the greenness of the green. Your question? No?
Oh, you asked what's the difference between centroid.
Oh, yes, with centroid and versus center mass.
So the centroid is simply the geometric center, correct?
Right.
And the center of mass is accounting for mass.
Yeah, so what he said is good. The centroid is the geometric center, whereas center of mass might differ. It might be a different, like a circle. Well, all of us have centroid, the center, right? But if the circle was lumpy, right, if it had more mass on the top than in the bottom, then its center of mass would be north of the center line. Yeah.
So like if you took a chunk of the helix.
What's that?
If you took a chunk of the helix, then the center of mass would be weighted more toward the top of that chunk.
Right. So that lumpy helix, we just work with the fattening helix. Its center of mass would be more towards the top than the bottom. Yeah, because most of its mass is up towards the 4 pi, where it's getting heavier and heavier, so to speak. Okay, so in short, the formulas for centroid and center of mass are the same. It's just if you're calculating the centroid, you take the mass, you can basically set the density to be 1, and you set the mass to be arc length. So but the formulas are essentially the same. So like if you want to calculate centroid, you just put density to 1, and you change the mass to arc length, and that's how to calculate the centroid. Center of mass, well, I have to divide by the total mass and integrate the density with respect to x and y and dz like that. These formulas will calculate for you the center of mass of a curve. They're just based on taking the Riemann sum and taking the limit as the Riemann sum goes to infinity for like the finite center of mass formulas from physics, but I don't think we need to go through that in here. Anyway, so like for this helix, let's see here. Is this a helix? Not a helix, right? What's z equals h? That's a constant, right? This is a circle at z equals to h, right? So what I'd say about the density, I said the density is 1, right? So I'm actually calculating centroid. So the mass is actually the arc length, isn't it? Uh-oh. Except I can't read my own example where I said 0 to pi, right? So it's not a whole circle, it's a half circle. Let me draw a picture over here. So we're looking at this half circle. Well, it's in the z equals to h plane, right? And it's going from, where is it going from? So my usual picture, it's something like this, right? think it's basically like this is the curve we're looking at here, right? So you can geometrically kind of tell where the center of mass should be, right? It should be somewhere along this line, maybe like here, right? Assuming constant density, the center of mass, if the density is constant, the center of mass is where the centroid is. They're this one and the same. So not surprisingly, we get the average x is 0, okay? And the average y is 2 pi over r. Z is constant, so like the z is h as well. I mean, if I integrate this with z equal to h, that gives me what? Think about how this integral goes. If you put z equals to h here, right? The h pulls out. We have the integral of the ds. What's the integral of ds? It's exactly the arc length again, and m is the arc length if delta is 1. So you get arc length over arc length. We just get h back again. But anyway, geometrically, it should be clear that the center of mass or centroid is on the z equals h plane here. So
if we did z equals, wait, going back to this parameter, yeah, if we did z equals t, then we could get the coordinate of the centroid as pi over 2.
So if I did z equals to, now you want to make the, what did you want to do?
So leave it the same, except that instead of having z equals h, you have z equals t.
But, so you want to look at the half a helix.
Right.
So then that would be something like this, right?
Would you end up with the same x and y coordinates? And then,
Yeah, that's a good point. The x and y coordinates wouldn't change. The arc length would change, though.
oh.
So, I'd have to work through it. Tell you what, let's try to work through this example tomorrow with a half helix, if I remember. But guys, that's the definition. Now, obviously, we need to do examples, right? You need to work examples to understand it. So that's what we'll do tomorrow. I will let you guys turn in your homework on Thursday because I want to give you time to ask questions about it tomorrow. If you want to take yours back, you can. Of course, you're done with it, but it's fine. And so I will be announcing the team captains for Math Battle tomorrow. And I'll try to assign teams. Do you guys, I can do it two ways. I can assign team captains and then let you pick your team, or I can just assign teams. What's your preference? Assign team captains, let pick teams. All right. Seems like a opportunity for awkwardness, but I'll go with it. What's that?
It also seems like an opportunity for balance.